Differentiation in mathematics is a process of finding the derivatives or rate of change of a function. In contrast to the abstract nature of the theory behind it, the practical technique of differentiation can be carried out by purely algebraic manipulations using 3 basic derivatives, 4 rules of operation, and a knowledge of how to manipulate functions. They both essential created integral and differential calculus. Newton was more involved with the speed of the falling object and Leibniz with the slopes of curves to illustrate the rate of change. Although they both looked at the different things, they both came up with the same result, hence the accusation of stealing the other's idea. However, combining both of their ideas, fundamental theorems of calculus was created, which links to the concept of integration to derivation. Many aspects of civil engineering require calculus. Firstly, derivation of the basic fluid mechanics equation requires calculus. For example, all hydraulic analysis programs which aid in the design of storm drain and open channel system use calculus numerical methods to obtain the result. In hydrology, volume is calculated as the area under the curve of a plot of flow versus time and is accomplished using calculus. In differential calculus, related rates problem involve finding a rate at which a quantity changes by relating that quantity to the other quantities whose rate of change are known. The rate of change is usually with respect to time. Because science and engineering often relate quantities to each other, the methods of related rates have broad application in this field. Differentiation with respect to time or one of the other variables requires application of the chain rule, since most problems involve several variables.
A light is at the top of a 16-feet pole. A man with 6 feet tall walked away from the pole at the rate of 5 feet per second, as shown in figure 3. The problem is, how fast is the tip of his shadow moving when he is 20 feet from the pole? Here's the solution. From figure 3, we can see that the two triangles are similar in shape. From that, we can make an equation of the big triangle equals to small triangle. So, it will be 8 over 16 equals to 8 minus x over 6. And then, we have to solve the equation until we get L equals to 8 over 5x. And then, differentiate L into dl dt. From the problem statement, we have known that the rate of dx dt is equals to 5 feet per second. Therefore, 8 over 5 will multiply with 5, so we will get 8 feet per second. Thus, the tip of the shadow is moving at the rate of 8 feet per second.
A tank of water in the shape of a cone is being filled with water at the rate of 12 meter cubed over second. The base of radius of the tank is 26 meters and the height of the tank is 8 meters. At what rate is the depth of water in the tank changing when the radius of the top of the water is 10 meters? Here is a sketch of the cross-section of the tank. We want to determine the dH over dt when R equals to 10 and we know that dV over dt is 12. The second step is we'll need to find the equation for the volume of a cone, which is V equals to 1 over 3 pi r square h. However, it has both r and h in it, and it would be best to have only h, since we need the rate when the depth of water is changing. Based on similar triangles, we get the following equation, which can be solved for r. R over h equals to 26 over 8, and then it will give us R equals to 13 over 4h, and then we will plug it in the equation and it will give us V equals to 169 over 48 pi h cubed. Next, we will differentiate v to the respect to h, which will give us 169 over 16 pi h square. And then, let's differentiate this with the respect to t, which will give us dv over dt equals to 169 over 16 pi h square times dh over dt. To finish off this problem, we need to determine the value of h. We already know the radius of the top of the water is 10 meters. So, we know that h equals to 4 over 13 r equals to 4 over 13 times 10, and then we will get 40 over 13. The rate of change of the height of the water is then 12 equals to 169 over 16 pi times 40 over 13 square times dh over dt. Therefore, we will get dh over dt equals to 3 over 25 pi. So, the answer is 3 over 25 pi meter per second.
The conclusion for the related rates problem question is, in related rates problem, we will be presented with an application problem that involves two or more variables and one or more rate. It is the job for the students to construct the appropriate model that can be used to answer the posed question. The conclusion to the related rates question. First step is we need to read the problem carefully and identify the quantities that are changing with time. There may be many quantities that are changing with time, so we need to try to identify which variables are important to your goal and only focus on these quantities. Second step is we need to draw a diagram if applicable and assign mathematical variables to each quantity that is changing with time. If you are given with a particular value of quantity that is also changing with time, do not include these values on your diagram. We will call this as instantaneous value of the variable. Third is relate the important variable using a mathematical model. Typical models are known as formula for area, perimeter, the Pythagorean theorem, and trigonometric ratios. It may be necessary to use more than one technique, such as similar triangles, to reduce your model down to one that only involves the variable of interest. Fourth step is implicitly differentiate both sides of the question found with respect to t. Fifth step is substitute in the known values of rate and known instantaneous values of variable. Sixth step is solve for the unknown rate. And lastly, write a full sentence of conclusion.